Hello, and welcome to this webinar presented by the IET's Cambridge Network. We represent members in the Cambridgeshire area, but we're very happy to welcome folks from around the UK and indeed globally tonight. My name is Phil Zerngast. I'm the chair of the local network and I'll be your host tonight. And before we get underway, I'll cover a few points of housekeeping. Now, we will take questions, but we'll leave the answers to the end of the presentation. So if you have a question, please use the Q&A button, which you'll find at the bottom of the screen next to the Zoom control panel. That's the Q&A button, not the chat button. We'll endeavour to answer all your questions tonight, but if we don't, our speaker has offered to answer those offline, and they'll be presented later on the IET's Cambridge Network website. We're recording the event tonight, and that will also be available if you look on our YouTube channel, which you can find by searching for IET Cambridge. Now, tonight, I've been asked by the IET to mention that it has a diversity and inclusion survey running this year, and I'll put some more details up on the chat panel a little bit later. And finally, I will mention that our next event is on the 6th of May by a company called Riverlane in Cambridge on the subject of software developed for quantum computing applications. Now, on to tonight's event. And I'm very pleased to welcome our speaker tonight, who is Lawrence Blakely. Now, Lawrence is head of software, mechanical design, electrical design, and hydraulic systems at Aerospace, Vertical Aerospace. Lawrence started out as an apprentice at Marshall's Aerospace here in Cambridge, and has more than 20 years experience now in systems design and manufacturing. That's mostly been focused in the aerospace industry, where he's worked on electrical systems architecture and installation design. He's had experience across the entire product lifecycle, from concept through prototyping, certification, and on into production. And he's worked on satellite launch systems on the A400M military transport and also on the A350 airliner. So without further ado, I will hand over to Lawrence Blakely to tell us about Vertical Aerospace. Thank you, Lawrence.
Thank you very much, Phil. Thank you for the kind introduction. I'll just share my screen. So hopefully that can be seen. Phil, please jump on if that isn't visible. So yes, I'm a product of the Marshall's Aerospace apprenticeship many years ago now, but it certainly stood me in good stead for the challenges that I face now, and I'm not going to be able to cover all of them, but I'm certainly going to touch on what I consider to be the bigger technical challenges that we face here at Vertical Aerospace. And it's going to centre a lot around the electrical propulsion system, which I guess makes a lot of sense, as that's part of the new area of development for eVTOLs. But before I do that, I will also cover a bit about Vertical Aerospace, our history. It's not so long, but I think we've covered quite a bit of ground in our short existence. We've had a guiding phrase. I think the wording might be slightly changing now as we're growing, but the philosophy is the same. Really, it's about developing technology to enable a lot more accessibility to personalized flights. So the whole concept of hailing a cab, a flying cab, really it's trying to make that a reality. The focuses we have here are to make it accessible, on demand, and carbon free. The company was formed by a guy called Stephen Fitzpatrick. He's the founder of OVO Energy. I think they're now the second largest supplier of electricity in the UK. And he founded that 10 years ago. And about 5 years ago, he wanted to start looking into how to electrify aerospace. And how to overcome some of the challenges faced by helicopter flight, because there is already a VTOL option, and why not just electrify a helicopter? There are some really good reasons why not to, and I'll touch on some of them later. But one of the things Stephen was really focused on is not just becoming another aerospace company. Obviously needing some aviation capability, so systems architecture. There's been a lot of electric flight development in the mainstream aerospace companies, and also the regulation side. But combining that with his current area of expertise with OVO around renewables, battery technology, the ground infrastructure area of our development is very well covered by his ability to provide electricity, but also coupling that with the fast-paced agility of Formula One and also automotive. So battery technology is really advanced in automotive, as well as motor design, inverter design, lightweight structures, crash capable structures is very much developed in the Formula One arena. So Stephen brought these different industries together and created Vertical Aerospace. Now, Vertical Aerospace started out really as six guys in a shed. It's almost a stereotypical kind of start point for this type of company, where it was 6 people playing around with whatever technology was available at the time, and the output of that was the we call it the proof of concept, the POC. We now call it VAX1, and that really was demonstrating that the technology, today's technology or 2017's technology, was good enough, and just good enough, but good enough for electric vertical takeoff and landing. And they created a vehicle. It was actually fairly capable. It could carry the payload of 1 person, although it wasn't sufficiently developed to actually put a pilot on it. Based on that, the company grew to, so in 2018, about 30 people. We started working on what we called Serif. We now call it VAX2. So X1, 1 person, X2, 2 people. You'll probably notice a theme running there. And we flew Serif. I will touch a bit on some of the technology and the development of Serif in a bit. But we also acquired a company called MGI, that is or I guess it still is a Formula One consultancy company, very much specialized in carbon composites development for the Formula One industry. And we acquired them and created Vertical Advanced Engineering. We grew again in 2019, finishing 2019 with about 70 engineers and a company size of about 110, something like this. So touching on the proof of concept, the POC, and now named VAX1. The challenge here was integrating already known systems together into a flyable 750 kilo full-sized vehicle, and flying this around Kemble Airfield. It was under the full coverage of the CAA, so it passed a number of checks to ensure it was safe to fly. But that it wasn't good enough to turn into a product. It didn't have sufficient safety levels in any of the systems, so any failure actually would have led to a loss of the vehicle. Thankfully, that didn't happen, but it's certainly not safe enough for aerospace. So from that, we moved to Serif, now VAX2. And one of the clear differences you'll see is the number of rotors. So we've gone from a quadcopter, a 4-rotor vehicle to 6 arms with 12 rotors. Now that's really focusing us on how do we create redundant systems? How do we make this vehicle tolerant to a failure of one of the propulsors? Now we did a lot of modeling around this, and we also successfully flight tested a failure of one of the propulsors. It was designed to fail 2 motors, but we decided not to push our luck on this vehicle, and we settled with just failing 1 motor and continuing safe flight and landing. But really, the challenges here were not just about developing that redundancy, but it's developing our capabilities. So we're growing as a company as well as developing our product. So we need to develop all of our tools, our techniques. Now the image you see, and I'll touch on it a bit in a second, it really shows the interaction of some of these systems. So there's the rotor, the motor, and then down the side of the arms that are supporting them is the cooling system. So the rotor is providing the cooling for the motor and the inverter. So there's a real close coupling of these systems. And that capability we needed to develop. We have to develop everything in-house, so we needed to develop that capability. And that's quite specific to this application. So we end up having to design our own rotors to meet this specific need. And here you can see the insides of that housing. It's nothing particularly special, but it's really showing the close coupling of the electrical connections, the cooling system. Obviously, we can't have any leaks. That would be quite problematic. So the care and the criticality of this installation is quite high. Now, what you'll see on the bottom left is a view of the airflow from the rotors. And what you'll see is there's quite a dead patch underneath the rotor at the hub, where you actually don't get very much airflow. So it was really important for these cooling pipes to be running along the length of the arms, because we really take credit of the fast moving airflow. And that's what I mean when we're having to couple the different systems together quite heavily to develop this capability. So just to look at that from a systems engineering perspective, we take an input. So we take the aircraft performance. So this is a target operation. In the case of the Serif, this is 2 people flying a 30-mile mission. We then have a mission profile for that. So a vertical takeoff, a forward flight period, a vertical landing. There would then be a go around, so an emergency aborted landing programmed into this mission. We have some of the flight dynamics, so the accelerations, how maneuverable we need the vehicle to be. So this could be how susceptible it is to gusts, or just is it a direct flight path, or are we having to maneuver around certain land features, mountains, buildings, whatever that could be. There's a number more in this list, but these are the kind of critical ones for the purposes of this. From that, we can then size the motor, size the inverter, and we can track back all the way to sizing the battery and the associated systems with the battery, as well as sizing the lift rotors. So now we know what torque we want the motor to spin at, what's in speed, what voltages we want to run, and out of that we get essentially weights, but not just weights. We also get some features for the control laws that we need to develop. So this could be how fast the motor needs to accelerate, or how fast it needs to decelerate. It could be some control loop speeds, but these elements are then fed out into the wider flight control system. Now, that in itself is all very nice, but these weights need to match the original requirements. So if when we sum up all of the weights of these systems, we no longer can put 2 people in the vehicle, then we don't have a closed loop. So we need to revisit this. Weight is exceptionally critical, as I'm sure you can imagine, for an aerospace company. So it's probably quite a basic view of how we're developing our system. But essentially, any engineering problem can be addressed by taking this systems engineering approach, and we don't do anything different in that respect. I'm just going to show you a quick clip of the outcome of our development on V8X2. You may have seen it before. It's on our website and YouTube, etc. But I'll show it because it's quite impressive. As I'm sure you can imagine, the first time that took off, it was quite a nerve-wracking few moments, but it completed its successful flight test campaign, quite notably before the City Airbus, although City Airbus, I think, went on to achieve slightly more than we did with our program. We decided that V8X2 had done enough and given us enough information to move on to what we are now calling V8X4. And I think the main event for the company for the next 3 years, probably. So to take a bit more of a look at V8X4, we are targeting to fly 100 miles at 150 miles an hour. Now we should achieve slightly more than that, so maybe 120 miles at a slower speed, or a shorter distance at a higher speed, around 200 miles an hour. But that's kind of in about what we're targeting there. All electric, as the name suggests, eVTOL. And we're targeting missions like shuttling from city centres to airports. This is a pretty standard target for us, where to travel this by car you're looking at an hour and a half probably, and here we can do that same journey in 20 minutes. 1 pilot, 4 passengers, and that's passengers with luggage. Really crucially, low noise. So just staying on London. London is limited on the number of helicopters that can fly from Battersea, actually, in the centre, because of noise. That is the limiting factor. So we reduce noise, we're quieter than a helicopter, we can get more flights. And also, quite critically, more affordable. We want to bring this type of transport to the masses. that means we need to be more affordable. We're targeting to be cheaper than a black cab, I think around $5. So what's that, £3 a mile, something like this. That's quite a step change for this type of travel. I'm just going to focus a bit on one of the real noticeable differences with this vehicle compared to Seraph. Obviously, we have wings now, rather than just a multi-copter, but we've also got articulated rotors or propellers or prop rotors, as we are now coining the phrase. So these have two jobs: propel us forwards and to maintain us in vertical flight. We're doing this through an articulated joint or tilt mechanism. So we have to move the electric motor through, it's actually about 100 degrees. So we want to go past the vertical to give us some elements of yaw control. And to do that, we've got to create quite I would say complex. I'm sure there's more complex joints out there, but it's complex through its need to be extremely robust. Any failure for this mechanism could be quite problematic. So we now add into our development this tilt mechanism. And just going back to our previous systems engineering view, this tilt mechanism is going to have an effect on how we're developing the motor, the inverter, and the associated cooling system. As we no longer can fit everything in one space, we have to spread out the design of those systems across that tilt mechanism. But essentially the process is the same. Now, just to give you a bit of a view on how we do that, or how we are doing that for the V8 X4. These are some test rigs that we have in our facility in the centre of Bristol. We call it the single rotor rig, which I guess is not a particularly surprising name. But here we are starting to look at the interactions of our new motors, new inverters for this vehicle. And actually this rig goes into a full test program, I think starting on the 26th of April or 29th of April, so only 10 days away. But we do a lot of systems modeling as well. And I talked earlier about developing systems as a whole. You can't develop these things in isolation. And really just to kind of make that point, in vertical flights, these rotors don't really interact very much. But as soon as we start going through transition, so this is the forward rotor tilting forwards, the wake from that first rotor is going to wash over the wing and interfere with the rear rotor. Now that gives two effects that we really need to take care of. One of them is it will affect the lift capability of the rear rotor, but the second is it's going to have a significant impact on noise. So as the turbulent air from the forward rotor is interacting with the rear rotor, that's going to be quite an increase in the noise signature of the vehicle. So we need to be very careful and very mindful of this as we're developing it. Now, I couldn't not talk about batteries. Batteries, I think, are probably going to be the larger challenge across the whole vehicle. The flight control system is particularly challenging, but batteries at this scale and as the main energy provider for the vehicle are new. So I will just jump into a bit of detail here. I get a lot of questions of why do we not just take a Tesla battery. Generally, everyone sees Tesla as producing the most capable automotive batteries. So why can't we take a Tesla battery, build an aircraft around it, and then fly it? Now, yes, Tesla make very good batteries, but they make very good automotive batteries. They don't make aerospace batteries. So a few of the focuses here that I would just draw out is there's no redundancy. Aerospace needs redundancy. You can't pull your aircraft over and step out. Unfortunately, you can in a car. So you have a failure and you stop, you get out. So no redundancy, that's the first problem. The second, although the energy density and power density is very good for an automotive, it's not the right balance for aerospace, and certainly vertical flight aerospace. For vertical flight, you need a lot of power and actually not so much energy. So we end up creating a very power focused battery rather than an energy focused battery. And again, the split in automotive generally isn't quite right. High performance vehicles, they're starting to move towards the high powers that we would expect to see. Cooling, automotive generally focuses on a liquid cooling approach. Now this might be okay for aerospace. There's nothing fundamentally wrong with using it in aerospace, but it's not necessarily the most weight optimized approach. Also, these battery systems are fully integrated into the chassis of vehicles. Now, our vehicles are different shapes, so that again doesn't work. And generally, most automotives are running a 400 volt system. Porsche are now bringing out an 800 volt vehicle, or brought out an 800 volt vehicle. I expect some more to follow, but at the moment, to really get the best volt to amp ratio, we need to be looking higher than the 400 volt. And then obviously it's not aerospace certifiable, it's only automotive. So where does that leave us? So Tesla, the Model S, which is what my numbers are based on, is looking at about 168, I think I said, watt hours a kilogram. Now Pipistrel, they have certified an aircraft, electric aircraft. It's conventional takeoff and landing, therefore they're not so focused on this level of improvement, this type of improvement. So they're in and around the 150 mark. There's the Rolls-Royce Excel program, again, about 150 mark. I've 1, 2, and 3, they are real numbers, but I've removed the company names just for IP reasons. And then, as you can see, we're really stepping up the game. This is our battery that we have in build at the moment, and I think we're looking at around the 230, 235 watt hours a kilogram, which is extremely credible. We're not the only ones in this region now. Some of our competitors are also looking at this region. Some have built battery systems around that. Now, a battery isn't actually that complicated. You get a load of cells, you package them, hopefully in a nice, neat array. You have some battery management, contactors to open and close circuits, and then you put it all in a box, and then you install the box somewhere in the vehicle. There's a lot of nuance to it, but essentially, and even if you reflect back onto the Tesla view of the battery, the construction is not the most complex. It's not a turbine engine. The problem with these is the failures are extremely volatile. And they're also very difficult to read. Getting data from, in this single pack, there's probably 200 cells, which I think it's 194 cells. Getting data from 194 cells is really very difficult, if not impossible. So it's not necessarily the physical construction of batteries that make them challenging. It's reading the data and understanding what we do with this data. And because you can't read everything, really we need to analyze and create system models of what's going to happen. So here we're looking at cooling and also impact and what that does to the battery system. So the top left, you can see some different types of cooling methods and how they affect the cells. Now this affects how cells age, how they degrade over time and in specific usage conditions. Now the bottom left, this is called the Bunsen burner test. We set fire to a pack and see what happens. Ultimately, we want to contain the fire. This was a baseline test where we were not expecting the fire to get to escape. Sorry, we were expecting the fire to escape. We didn't make any effort to contain, but we wanted to see what the worst case was and what we had to contain. We need to make sure that if we drop it, it doesn't firstly spontaneously combust, but secondly, it still needs to be safe. People need to be able to handle these packs if they get dropped. So that's part of the test. And here in the bottom right, this is called an outgas event, which normally is a signature for there being a thermal runaway. So these are some of the elements that we have to model and then have to test to prove out our models. It certainly provides some of the more entertaining testing that we get to do at Vertical. Now looking at the modeling, I will notice it's hypothetical data. So I'm sure there'll be a few people that are taking some of the power numbers that are portrayed here, but they're not, they're for the purposes of this presentation, I will stress. So through our modeling, we need to try and understand what is going to happen to the battery. Essentially, how hot is it going to become? The temperature is really the key for designing batteries. And what you can see in the graph on the left is a mission profile with some powers attributed to it. So we have a takeoff. Takeoff is very high power because we have to get over what's called ground effect. That's only a couple of meters worth of climb, and then we're in the more steady climb, which is slightly low power. And then when we're in hover, we're not accelerating upwards anymore, so again, low power. As soon as we yaw, the power level increases. We then stop that yaw maneuver and we hover, so we drop down to the lower power level for hover. And then in this mission, we reverse, descend, obviously not as high as the climb level, but we still need a significant level of power for controlling the vehicle. And then the deceleration, this is again combating the ground effect just before touchdown. And as you can see on the cell temperature and the busbar temperature, we run to just underneath the 65 degrees C cutoff for the cell temperature. So this is good. The middle, we simulate in the model a failed rotor. That puts a lot more effort onto the battery. So the failures here at the beginning of the hover phase, sorry, the beginning of the yaw phase, we continue the mission, but in that second yaw, we're now over temperature. So now we could consider that probably an outgas event could occur. It could go directly into thermal runaway, but we're now moving into quite a bad part of the battery's capability. And again, on the right-hand side, this is a sub-pack. So we use multiple battery packs. This is a failed battery pack. And actually, in a failed battery pack instance, we need to use even more power in some of these maneuvers. Again, we go over the 65 degrees. So in this situation, I would say the battery is not good enough for an aerospace application. Although we can do standard VTOL flight, we can't tolerate a failure. So in this instance, we go back to the drawing board and modify probably something around the cooling, maybe look to reduce the weight of the vehicle to take away some of the need for this level of power. Something else with the battery, which isn't obvious in the outset. So here we're looking at the state of charge. So I mentioned earlier, predicting the state of charge is quite difficult. And really this is why. I'm just going to go through some of the build-up of this. So the full length of this battery, that is 100% of the battery charge that we can use. So starting at the bottom, we take away a portion for to always have a minimum amount of power in the battery. So this is the minimum amount of power we need to safely get down onto the ground. So I've removed that because we can't use that during a flight. That's in extreme circumstances. Now, now I remove also what's called the reserve requirement. So on the previous slide where we had that failed sub pack, the remaining sub packs need to be able to take up the slack from that failed sub pack. So that's that portion up to the reserve requirements line. We need to balance the cells. Now when you drain the battery pack, some of the cells will become out of balance, so we need to take into account that tolerance. Now, depending on how we measure the cells, then we could measure every single cell, in which case the accuracy of our BMS system will be really, really good. So let's say that's 5%. If I don't measure very much of my battery pack, my accuracy is going to be a lot less. So let's say that's 30%. And I'm probably going to be somewhere in there because wiring up 200 cells per pack is not so practical. Wiring only one cell up is also not practical. So we're going to be somewhere in this, between this 5% and 30% of the BMS tolerance. So my minimum state of charge is now, in worst case, at that 30% line. Now going to the maximum state of charge, I need to remove two things from the top. One first is lifetime. So I talked earlier about the degradation of the battery packs, and I need to remove that from the top because at some point my battery is gonna degrade, and when it's at its end of life, I still need to be able to do the mission I've promised the operators we can do. So automatically I have to take that away from the 100% charge. And then secondly, I need to remove this balancing tolerance again. So in any battery system, the available energy is then what's left between here the 30% and here the balancing tolerance. So clearly I've got tunes I can play around the BMS tolerance. There's not much else I can play with in this diagram to try and optimize my battery design. Now in the battery system construction, I think my first point I will note is when you hear numbers being talked about by companies, so I will stick with Tesla. They're not a competitor of ours, but they talk about batteries with maybe a watt-hour kilogram of 380 or 400, I think I've seen recently. Generally, they talk about the cell. Now, what needs to be taken into account is the whole system, because it's not just the cell, it's all of the packaging, all of the bus bars, all the electronics that then come together to make the system. So that 400 watt-hour kilogram, it won't be 400 watt-hour at car level. It'll be somewhere, maybe if they're lucky, around the 260, 270. It might be slightly higher, but it's certainly not going to be 400 watt-hours once it gets integrated into the system. So here you can see the cell has a huge impact on the mass. So this is the right-hand pie chart, but it's not the only factor. The casing, cooling, being the majority of the rest of the mass, and then the rest is made up in the smaller elements. But the cell cost is a huge part of the battery system. and it's a real driver for the whole economics of the vehicle. So I guess it's quite obvious in saying we need to really focus on maximising the use of those cells, and also then minimising the costs for the other areas. We can't change the cost of the cells so much, but we can have an effect on the other areas. So reducing the outer casing, reducing the cooling system being the two second major, and then the electrical distribution, really this is the bus bars. So being more clever about the bus bar design to reduce the cost is key. Now I can't touch on batteries without talking about the aerospace regulations. So batteries are new as the primary source of power. There obviously are batteries in aircraft, and batteries are used as backup power, but they're not the primary power provider for aircraft. So a new standard has been created. So it's actually what's shown in the middle for aircraft design. So this is special condition vertical takeoff landing, or SCVTOL is what it's commonly known as. Now this special condition sits within the already existing framework of aircraft company adherence to the regulations. So this is also known as Part 21. There's nothing changed with this, but our company that we're developing, Vertical Aerospace, we are set to this year become a DOA. It's now under the CAA, but the CAA are using the EASA rules at the moment. And then on the right, I've just highlighted one of the main documents that is under review to that we need to certify our batteries to. This is a document that defines the acceptable means of compliance. If we have a battery that passes that document, then it's very easy to demonstrate that we are compliant to the SCVTOL requirements. It doesn't mean we have to pass everything. It's just we need to demonstrate an alternative means of compliance if we can't meet the acceptable means of compliance. There's another whole host of documentation that is being developed as well that run alongside the DO 311A. So I'm sure there'll be lots of questions on batteries. I can't see the questions coming through, but I'll look forward to touching on some of those, I'm sure. So just to kind of touch onto our future before I do move over onto the questions. This year, so last year and this year, we are designing and building our prototype of VA-X4. It extends into 22 because that's where the flight test campaign is going to run through its majority. But we should be flying. I should have a video by certainly by this time next year, but by the end of this year, we should be flying. 2021 will be a big year from the authorities' perspective. We expect to get our design organisation authority. So this is demonstrating to the CAA and that we comply with the requirements of that first document on the previous slide. POA is the Production Organisation Handbook. So authorization, and that is in a similar vein to the DOA. Then we intend to move from our prototype vehicle to our certification standard vehicle. To the untrained eye, the vehicles will look the same, but we will modify some of the internals to improve, hopefully, and make it certifiable. And that certification period will run through 2023 and 2024. Through that period, actually, we will start some operations. They will be on restricted segments, so they'll be quite specific. And then we'll enter into more standard operations in 2025. I think that brings me to the end of my presentation. Thank you very much for listening. And Phil, I think I'll turn back over to you to manage the Q&A.
Okay, thank you, Lawrence. And we do indeed have lots of questions, lots of battery questions, lots of safety related and control questions. So I will hand over to my colleague, David Blake, who will take you through the questions. Thank you.
Well, thank you, Phil, and thank you very much, Lawrence. I found that most interesting. I hope you can all hear me okay. As Phil said, there are lots of questions, and they really go into two areas. One is about the operational side, and the other is about the batteries and the electrical systems. So I'll start on the operational side because they were the questions that came up first. There's a question about this whole affair looks very amazing. If this kind of electric flight takes off, how will air traffic control handle the greatly increased number of flights? I mean, have you considered, loads of these aircraft flying into London City Airport, for example?
Yes, absolutely. And it's a very good question. And I can't say that today we have an answer. Now, I can talk about where we're focused. There needs to be a higher level of, I guess, automation around the air traffic control. We are in a government-funded development for this specifically, which is called the Future of Flight Challenge. And we've partnered with Bristol Airport, as well as a number of other companies to really focus on how do we develop that capability. So if there's 1,000 vehicles all coming into in and out of Bristol Airport, how is that managed from an air traffic control perspective? It's a very real challenge. Like I say, I don't have the answer, but we are specifically focused on that.
Okay. The test flight you showed was in calm, very clear weather.
Yeah.
How does your platform cope with wind, rain, or other unexpected wind conditions?
I don't know. For the vehicle that I showed, we were limited on the weather conditions from the CAA that we could take that vehicle in. For V8X4, we have to comply to the same standards as your CS23 aircraft from a weather condition perspective. I'm sorry, I can't remember the gust numbers, but there are specific gust figures, specific figures for rain, and we need to comply with all the same standards. So it's more of a challenge actually for the multi-copter. As soon as we're in conventional flight on the wings, it's pretty well understood. It's that vertical flight section.
Okay. Do you see an upper limit to the X? In other words, you're going up to X4. Will there be an X10, for example?
Very possibly. I think it will be around 2023 that we start focusing on the next vehicle. The current view is kind of two trajectories. One of them is to increase the payload. So it'll probably be 6 passengers first, not 10, but certainly pushing the limit on the payload. And then secondly, looking at what we can do to increase the range of the vehicle. So I know that they are linked, but from a payload perspective, you're looking at power when it comes to the batteries. When you look at the range of the vehicle, it's more the energy from the battery side. So this is where we do really trade the power and energy that a cell can provide us.
Okay. There's a question about if you lose one of the propellers, lost one propeller during takeoff, how does the aircraft actually respond to that?
So from a regulation perspective, we need to be tolerant for any loss and any single loss. Now, from a response perspective, during transition, the other rotors will need to take up the load. So the rotors, the motors, the cooling systems, the battery systems, depending on how we do the architecture, need to be sufficiently oversized to take over the load that is lost through that one loss of propulsion.
Okay.
The transition is certainly the hardest part of that. In vertical flights, you lose one rotor, so that's 1 lost out of 8. Now through transition, if we lose one, certainly one of the forward rotors, we lose both lift and forward propulsion. So that's likely to be the sizing case for when we define the rest of the systems.
Going further on from propellers and rotors, are they fixed or variable pitch?
So the forward rotors are likely to be variable pitch because they do the role of a rotor and a propeller. So they're two different duty cycles, as I'm sure you can imagine. So they're likely to be variable pitch. The rear propellers are likely to be fixed as they're only doing one job.
Okay. And what's the stall speed in forward flight mode?
Ah, good question. It's difficult to answer, because in theory, the stall speed is 0. Now, if we didn't rotate up the front rotors, you're probably looking at about 60 miles an hour, maybe 50 miles an hour. It'll be within that range.
Okay. And combining a couple of 3 questions, there's a question about whether you sort of took any inspiration from the Osprey. And following vertical takeoff, the craft transitions to forward propulsion held aloft by wing lift. What are the critical stages and related time windows for this transition?
So in the first instance regarding the Osprey, there's not a huge amount of read across actually. So there is some around the interaction of the weight from the rotors on the wing, but the tilt mechanisms are very different. They're engines on the end of the wings, so it's quite a different application. Sorry, can you just repeat the second question, Dave?
Yeah, so sorry, I'm looking at umpteen things at once here. Following vertical takeoff, the craft transitions to forward propulsion held aloft by wing lift. What are the critical stages and related time windows for this transition?
So really what is driving that is we want to minimize the time the vehicle is in vertical flight, because that really uses up the batteries most. As soon as we're in forward flight, the lift provided by the wings alleviates so much from a battery load perspective, but also from a motor an inverter load perspective. So the criticality is to transition as fast as possible, because that protects our vehicle, enables a greater range, minimizes temperatures. I wouldn't say there's any particular phase that is exceptionally critical.
Okay.
You might have noticed in the video, right at the end of the video, the vehicle's twitching slightly as it's landing. Now that's because we're entering ground effect. This is where air is circulating back off the ground and interacting with the rotors. So that's probably quite a critical phase, but we're close to the ground, so that would just lead to a bit of a bumpy landing if that's not managed properly.
Okay.
And the transition is really the critical part from a flight control system development perspective.
Okay. Right. Can this vehicle auto-rotate like a conventional helicopter in the event of
No, it can't. So the auto-rotate function is really linked to the inertia that's in the rotors on a helicopter. We don't have anywhere near that level of inertia in our rotors, but because we have multiple propulsors and we can cope with the loss of a rotor. From a safety perspective, you lose a rotor, we don't have to land immediately. That auto rotate, I would say that is a controlled descent, a controlled hard landing. Let's say, I don't want to use the word crash. It's a controlled hard landing. Now we are actually still within standard operation when we lose a rotor. So from a safety aspect, that's why our vehicles are more safe than a helicopter.
Okay. Couple of questions to finish off on some of the operational side is do you feel that you need a pilot, or in fact, can this all be automatically controlled in some way? Particularly the VX2, was this sort of on auto control, unmanned aircraft or not?
So the X2 was remotely piloted. that's certainly a possibility. Now, really, the position of the pilot is more to satisfy the authorities in the first instance. This is a brand new type of vehicle, and for the authorities, it's just a step too far to be a fully autonomous vehicle as well as a new type of vehicle. So I would say that we are limited by regulation at this point in time, rather than the technology. Now we're in another government-funded bid called CESAR, and CESAR is specifically looking at elements of autonomy within this type of vehicle. It will come. I think it's probably 10 years away before we'll see autonomous flight being certifiable.
Okay. A question here on the batteries, starting on the batteries. Not being able to use 25% of the battery capacity really means a lot of dead weight.
Yes.
Can that be improved at all?
I hope so, yes. So that some areas that we'll look at improving that are around being clever about how we measure the battery system, and then the predictions of what those measurements lead to. It's an area that we are specifically focused on. I think there is opportunity, absolutely.
Okay. Was solar power ever considered? Was hydrogen ever considered? You know, do you have a hybrid power system?
So solar was considered, but to provide low voltage power. So we generally convert high voltage to low voltage for the rest of the systems to use. Now we could use solar power for that. I think we might look at that again. Hydrogen, we've also explored what that might mean for the vehicle. A hydrogen system is way more complex. If you reflect back onto the simplicity of the battery system, it's no more than some cells, a buzz bar and a box, really. The hydrogen system is a lot more complex. So really looking at getting a certified product to market in a short time frame. Batteries were the obvious choice from the main propulsion, and DC-DCs going from high voltage to low voltage are already pretty known, whereas using solar power as primary power provider, again, we wanted to make our lives as easy as possible, considering it's an extremely complex vehicle. Yeah. So just focusing on the battery development in the first instance was chosen.
Okay. It's about how you use the batteries. So are you going to have, for example, any electronics or charge control systems in the pack? So you actually integrate sort of controllers into the pack?
Really, what I would say is our focus is on making the batteries as capable as possible and as lightweight as possible. So if including it into the pack means that we can use more than 25% of the battery, it earns its way on from a performance to weight benefit. If making the pack more clever doesn't increase that 25%, then it's just added weight, in which case it wouldn't go on. So it's really focused on that trade of gaining performance versus the weight that it would introduce.
Okay. Are you working with university chemistry departments to find a new lightweight power dense material?
Interestingly, a little bit, but it's not necessarily the main focus. We're not big enough in the battery world to really command very much. So we of course are keeping our ear to the ground, and we have great connections with some universities. But I really want to use battery cells that have known capability to then certify. If I was taking a cell out of a lab, that's a long way away from being production ready and operational ready. Yeah.
How do you envisage the batteries being charged? I mean, we can't come along just fill it up with some AVCAT or something or other like that. Are you going to have separate battery packs that you drop in, or are you going to have a fast charging system?
That's a great question. So if you look at Volocopter, I think they are going down the battery swap approach. Now, we could be looking at somewhere in the region of a ton of battery for our aircraft. And particularly as we try and make it as lightweight as possible, it will become more and more integrated into the aircraft. Making them swappable goes against that trend of making them lightweight and integrated into the structure. So I don't think, maybe we could do it, but in the first instance, I doubt we'll focus on making them swappable. So really the challenge comes into how do we charge them as fast as possible?
Okay.
And there's a lot of power to pass through a charge connector there. So I would say that is another area of technical challenge that we will face.
Yeah. Since here, most batteries seem to involve lithium, are you going to be looking for something else other than lithium because of the sort of environmental concerns of sourcing lithium?
I totally agree with the environmental concerns for lithium, and we're extremely conscious of securing a good supply chain. Lithium really is the option that is available at this point in time. I guess reflecting back onto my previous answer about other chemistries, I expect other chemistries to become available at some point in the future, in which case we will switch if it provides significant benefits, both morally from that supply chain perspective as well as aircraft performance.
Okay. Can you say something about how the work's funded? There's great interest in the fact that you've got 120 plus engineers. They obviously need payment. So
yes, they do.
How do you keep it all going?
So we have been lucky enough pretty much until this point, but continuing on from here as well, to have a founder who owns the second largest energy company in the UK. That's also growing outside of the UK. He's extremely passionate about our project, about our company, and totally believes in what we're doing. So he's self-funded. At least he's self-funded us up until this point. We will need investment as we move forward. Now that investment is coming part in our partnerships that we're pulling together. So working with Honeywell, working with Rolls-Royce, they're not supplier contracts, they're partnerships. So they ultimately take some of the burden of that development. But of course, we'll need funding to realise the full project.
Okay. Maybe just say something about the perceived maintenance issues. Do you feel it's fairly simple to maintain? And have you got any experience yet of keeping it going?
I mean, we have experience from keeping the prototypes that we've built going. Now, really, this is one of the key benefits of this vehicle, and this is one of the elements that drives down that cost per mile. Maintaining a gas turbine, for a helicopter, you're looking at $1 million a year, maybe, to maintain a gas turbine. I'm talking of a fairly good capability. Now, when you look at an electric motor, there's really nothing to it. It's easier to just replace every 5 years than it is to really maintain it. The battery, again, you just replace these things. End up being really cheap to maintain, and then cheap to replace compared to a standard gas turbine.
Time's getting on, and we'll be told by Phil how we're getting on, but I've got a few more questions here. Have you considered using the heat generated by batteries over flight surfaces and rotor blades to generate an increased lift capability?
We certainly looked at, I don't think we've looked at that specific use case, but we've certainly looked at using the heat in some areas and also the cooling effect of other areas and how we can maximize those. In some instances, we do use that heat differential but generally it's quite weight costly to move heat around a vehicle, certainly the vehicle of the size that we're building.
Okay, and you mentioned CEA and EASA. What about FAA? Are you involved with getting certification through FAA?
Yes, we will certainly look for certification with the FAA. How it works is there's a bilateral agreement with the EASA and the FAA. So generally, if we certify to the EASA standards, we'll get certification with the FAA. There's often a few tweaks that need to happen, but from a broad brush perspective, you get one, you get the other. But actually at this point in time, the EASA is requesting the more stringent requirements, certainly around the battery system. So our view is certifying with the EASA puts us in a much better position compared to some of our potential competitors that are developing in the States.
Okay. Has anybody actually piloted, physically got in the aircraft and flown any of them yet?
Our competitors, yes, they have flown. For us. Our VA X4 will be piloted, but by the end of this year, so they haven't flown. We've got a flight simulator that's linked to the actual flight control system, and we're certainly racking up the hours on that system at the moment.
Okay. And a question, are large rotors more efficient than small rotors?
Yes, they are. So more efficient, really, in virtue of you get a more of a disc loading. So either one large rotor, lots of smaller ones, you would need to cover a larger space. But large rotors are not very good when you're moving into forward flight. You get effects that the advancing and the retreating blades are acting differently in the airflow. Helicopters deal with this by actually trying to speed up one side and slow down the other to try and counteract that effect. But that's one of the limiting factors of the forward speed of a helicopter. So to actually overcome that, you need smaller rotors.
Okay. Now, just end up with one question. Have you considered supercapacitors to augment the battery for takeoff?
Yes, absolutely. From a weight perspective, they didn't buy themselves on. We're certainly keeping our ear to the ground with that technology, as at some point it could become interesting. Okay.
Well, I think you've been very, very good at answering all these questions, and Phil's popped his head up there. So perhaps it's time to let you go and get a cup of tea.
Thank you. And some really good questions there as well.
Thank you, Lawrence.
And there's still quite a few left. And thanks, Lawrence, for offering to answer those offline.
No problem at all.
I would just say that one of your colleagues here, Frederick Malaret from France/Italy, keeps popping up saying the very exciting presentation and best regards to you.
Oh, thank you very much, Frederick. Thank you. I enjoyed presenting. It's a pleasure to be invited.
Yeah.
Indeed. Thank you very much, Lawrence. It's fascinating to see behind the scenes, perhaps under the bonnet of your product development and the journey that you're on with what's likely to be a disruptive technology. And it's good to see that it's a British company that's sort of innovating in this space, and there's a lot of exciting development going on. I'm sure everyone on this call tonight would wish you good luck with the development in future. And again, thank you for taking the time to present to us tonight.
My pleasure. Thank you very much, Phil.
Okay. So that brings us to the end of tonight's event, everyone. So thank you for attending, and I hope you all enjoyed it as well. Please keep an eye out for our future events. So you can find them by looking on the IET Cambridge Network website. And as I said at the beginning, we will make available the presentation, the video, and the Q&A session. But that will take perhaps a few days to a week to get that available to you. So on behalf of the IET Cambridge Network, I'd like to say thank you for joining us. and I will leave you now with the more details of the IET diversity survey that is running. And you can all disconnect now. Thank you.